Mass of 62 kilograms is running at 3.2 meters per second when he decides to pass the runner in front of him. Speeds up to 4.1 meters per second to do so. A, how much work does Dave do to speed up? B, if this speed increase happens over 3.5 meters, how much force does he apply? Okay, so Dave, running at 6.2. Sorry, 62 running at 3.2. And he speeds up to 4.1. And he does it over 3.5 meters. Okay, how much work does Dave do to speed up? Again, I'm focusing on this equation here. This is an example where FD would not work. The reason FD would not work on this one is because I don't know the force, and until later I don't know the distance. And no, you can't do mass times gravity because Dave's going sideways. He's not going up and down. Yeah. Down here. Sorry. Yeah, I haven't gotten there yet. Yeah, sorry, omniscient narrator knows how the story goes. Yeah, that's where the 3.5 came from. Good question, thank you. All right, so we're looking at this equation. Work causes an energy change. And remember, when we're talking about energy change, we're talking about final minus initial. Just like last unit, when we talked about delta P, we talked about final minus initial. Same thing, no difference here. So again, just like in the last problem up here, I got to think about what is changing, what energy is changing. In this case, it's not the stored energy. He's on the ground. His stored energy isn't changing. When he goes forward, he's still on the ground. None of that has changed. So there's no stored energy change. What is changing is his motion energy, because he was going 3.2, but now he is going 4.1. So when I talk about delta E, I'm talking specifically about KEF minus KEI. That's where I say on these problems, you kind of have to think a little bit. Not like an insane amount, but a reasonable amount of thinking. Like, what type of energy is changing? What type of energy is changing here? Okay? And I'm just using this equation. So delta E is final minus initial. Energy is kinetic plus potential. So since there's no potential change, he's on the ground, there's no potential energy, I just do the kinetics. Just final minus initial for the kinetic. So work is what I'm solving for. KE final. So kinetic energy is 1/2 mv squared. So I do 1/2 m v squared. Now the velocity I need is the velocity at the end. Final velocity, final kinetic energy. So I need the 4.1. How fast is he going at the end? So that's 4.1 squared. It's only the 4.1 squared. It's not the whole thing squared, just the 4.1. Minus the initial, 1/2 times mass times the initial velocity at the beginning, which is 3.2. All right, 0.5 times 62 times 4.1 squared, 521.11 minus 0.5 times 62 times 3.2 squared, 317.44. Subtract those from each other and you get the work equals 203.67 joules. So Mr. B, how did I know to do the delta E? How did I know not to do the FD? I didn't know enough to do the FD. I didn't know about that. The other way is, what did it give me? It gave me velocities, which is kinetic energy, motion energy. So I was given motion, so I used motion to solve it. And B, if the speed increase happens over 3.5 meters, how much force does he apply? So now I know what the work is. The work is 203.67. Now we can use the W equals FD. So 203.67 equals F times 3.5. Divide the 3.5 over. And you get F equals 58.2 newtons. Now, could you go the other way? You absolutely could. I could give you the force and the distance and ask you to find the final velocity. Not that I would give you a problem like that where I gave you the force and the distance and ask you to figure out the final velocity. I would never do that. But like something in number 3, right? Number 3 is that kind of an idea. So you can go either way on these equations. You can find the work given the energy change, or you can use the work to find the energy change. Either way is going to work out either way the same. Okay? So here's what I want you guys to do. I want you